Hello and welcome to the Postcard Professor, where we take complex ideas and explain them in the space of a postcard.
This is the first on a series of lessons on heat transfer. The first lesson is going to be talking about conduction. And to simplify it down, we're only going to be looking at one dimension, and we're going to be looking at it in a Cartesian coordinate plane. In order to make a one-dimensional domain in Cartesian coordinates, probably the easiest thing to do is to look at a slice of a very large domain. So what we can do with this is we can say that this slice has an area A, but the width of this slice is very small. And so we can call this width a delta x, with that delta just telling us that we're looking at a very small region. Conduction and heat transfer is all about conservation of energy. And in the past, in your previous classes, I'm sure you've talked about a lot of different types of energy. Potential energy, kinetic energy, we can talk about nuclear energy, we can talk about chemical energy, and then the thing that we really care about here is thermal energy. So potential energy, is just mass times gravity times whatever height an object is at. Kinetic energy is 1/2 mv squared based on the velocity of the object. Our thermal energy is going to have the same m term, and it's going to have a constant, C, which is multiplied by our temperature. So the thermal energy, of course, is just based on the temperature of an object. Now the C is the specific heat, and it has units of joules per kilogram Kelvin. So this object here that we're looking at, or the slice of the object that we're looking at, has some energy associated with it, which is equal to this mCt. But if all we had was energy, we wouldn't have much of an equation. So we need to have some heat flux coming into and out of the object. And we're just going to draw that as a q dot in and a q dot out. So this q dot is what we call heat flow or heat transfer rate, and it just has units of watts. But we can also write this, can simplify it down, and talk about a lowercase q multiplied by our area. Now this lowercase q is a heat flux, and it has units of, as you might have guessed, watts per meter squared. So we have the energy of the object, we have heat flow in, and we have heat flow out. What conservation of energy says in this situation is that the change of energy with respect to time of our object here is just going to be equal to all the heat coming in minus whatever heat is going out. So based on what we already have, we can simplify this equation down. Instead of E, we can write mCt. So we have the change of this mCt with respect to time is going to be equal to, and here we can write this as a lowercase q in minus a lowercase q out, all multiplied by our area. So let's continue to simplify. We're going to move this m and c outside of the derivative since both of those are constants. We also know that our total mass is just going to be equal to our density of whatever our material is multiplied by the volume. And our volume, we can rewrite, since this is a nice rectangular prism, as our area multiplied by our delta x. So we can rewrite this equation as rho times A times delta x to take care of that mass term, multiplied by the c, which is another constant, and all of that multiplied by our derivative of temperature with respect to time. And then for now, our right-hand side is going to stay the same. But we now have an a on both sides, so those can cancel out. And on top of that, we can divide through both sides by this delta x term. And these x's will cancel out. And so our left side is pretty simple. And this right side should hopefully trigger you to remember some things from calculus. Because if we go back to calculus, we know that a function at some position x plus h minus the same function at a position x divided by h as the limit of h goes to 0 is simply the derivative of f with respect to x. So if we apply this using q instead of f and delta x instead of h, we can say that the limit as delta x goes to 0 of q of x plus delta x minus q of x over delta x is going to be equal to the derivative of q with respect to x. We're going to treat this q in over here as q of x, and we're going to treat this q out as q of x plus delta x. And so what this means is that this entire term here can be written as a negative derivative of q with respect to x. That negative comes in because what we expect to have is a q out here and a q in here. So rewriting this yet again, we're going to have a rho c change in temperature with respect to time is going to be equal to a negative change in our heat flux with respect to x. Now our next step comes about because we really like this to be all in terms of our temperature. So we're going to apply a law known as Fourier's law. And this is, of course, Fourier's law specifically in one dimension. And what Fourier's law says is that our heat flux is going to be exactly a negative k times dt dx. This k here is the thermal conductivity, which has units of watts per meter Kelvin. And by plugging this in, the right-hand side becomes a positive k, since those negatives cancel out, times the second derivative of temperature with respect to x. And this is a pretty good form of the equation, but the last thing we're going to do is just isolate our time derivative. So moving that rho c to the right-hand side yields a k over rho c times d squared t over dx squared. And we often write this as an alpha d squared t over dx squared. This alpha is just equal to this k over rho c, but this is called the thermal diffusivity. It has units of meters squared per second, which happen to be the same units as kinematic viscosity, which was the new that you get in fluids, in fluid mechanics. All right, so we have an equation. This right here is conduction in 1D. Now, this is a class of mathematical problem called an initial value problem, which is a little difficult to solve for what we're doing, especially because we're talking about an initial value problem that has a spatial component as well. So what we're going to do is we're going to simplify this. And the way we simplify it is by introducing an assumption. That assumption is that we are looking at a steady state problem. And really all that steady state means is that any changes in time have stopped. There might have been some transients in the past, but we've reached a point in time where nothing new is changing. The way we can write this is just that the time derivative of anything is going to be equal to 0, which means that our left-hand side over here is equal to 0. So if our left-hand side is equal to 0, alpha is a material property, so it can't be 0. And so we should end up with a d squared t over dx squared should be equal to 0. Well, now this is something we can solve, because all we need to do is integrate with respect to x. So if we integrate once, we get that the change in temperature with respect to x is a constant. We can call that constant a. If we integrate again, we get that our temperature as a function of x is going to be equal to this a times x plus some unknown b. So this is our solution. This is our general solution for 1D conduction. So what we need to do with this to apply it to a specific problem is determine what our boundary conditions are. So our three boundary conditions could be our temperature at 0, our temperature at L, so the temperature at some length of our full domain, and the Q. I only have a single Q here because our Q is based off of the temperature derivative with respect to x, which we know is a constant. So if we're given Q, we can find out A directly. So our A here would have to be a negative Q over K. And this just comes directly from solving for dt dx from Fourier's law. If we are given our temperature at 0, then this is just going to be B directly. If we take the temperature at 0 here, the A just goes away and we end up with B. So if we're given Q and the temperature at 0, then it's very easy to plug things in. If we're given Q and the temperature at L, well, that's a little more complicated, but it's still not too hard. And if we're given these two, maybe the easiest thing is to calculate Q. So Q is also going to be equal to a negative K multiplied by our delta T over our delta X. Again, that just comes from Fourier's law, but we can rewrite that as our Q is equal to a negative K times that temperature difference, right? So the difference between the two ends divided by our delta X is just our full length. And this works because we know that Q has to be a constant. So as a quick review, heat transfer is going to be based off of the conservation of energy. If we're looking specifically at 1D Cartesian, we can draw our domain as a little slice, a rectangular slice of some larger length. We can check the heat flow coming in and heat flow coming out, and that should be the change in energy in our domain. We end up with a nice clean solution to all that by using just basic calculus plus Fourier's law. Once we get here though, this is still a little difficult to solve. For now, at least, we're going to be looking at just the steady state solution of this, which means that any changes in time go to 0. And then the change in temperature with respect to x, we can write that directly based off of the heat flux, which for this problem, the 1D Cartesian, has to be constant in x. And then based on that constant A, we can very easily write the full temperature profile, meaning that we can know the temperature at every point in x. I hope you enjoyed this video, and I hope that this provides a good start to your understanding of heat transfer.